microwave oven, it's the exact same thing. Then infrared radiation is radiation given off by warm objects. Your body gives off infrared radiation. Certain snakes can see infrared radiation, and that is how they find their prey that they have to catch and kill and eat. Okay, so infrared radiation is heat waves, basically. Then we get the visible spectrum. Our eyes are sensitive to red, orange, yellow, green, blue, indigo, and violet. Some people are a bit of colorblind, so they can't distinguish between blue and green, maybe. And you get various grades of color blindness. I'm not going to go into that, but this is the visible spectrum, and this is how we see the world around us. All right. After violet light, we get something called ultraviolet light, and most of you should know about ultraviolet light. If you are exposed to too much of it, it causes skin cancers and cataracts, among other things. It is the one that causes sun tanning, and that is why we rub on block out if we know we are busy out on the sports field the whole day. Okay, it is to filter out the ultraviolet light, because too much ultraviolet light, it's becoming fairly high energy, it can cause damage. Okay, after ultraviolet light, we get X-rays and gamma rays. Then we had a look at, did we do the refraction of light? Yes, we did. And we said, why does the red light form always at the top and the violet at the bottom? Red has the longer wavelength, it is refracted less. It's slowed down less than the violet light. Yes. Okay. Now, in terms of sound, when we start looking at sound waves, people, everything holds true in terms of reflection, refraction, diffraction, and interference. Okay, sound is a wave. If it is a wave, it can be reflected, refracted, diffracted, and interfered. So, sound, in this case, we've had a look at all the waves up to now were transverse waves. Sound is a longitudinal wave. Can you remember when we did wavelength and amplitude? We had a look at the wavelength and amplitude of a longitudinal wave. We also say sound is a mechanical wave. It differs from X-rays and violet, ultraviolet light and visible light in the sense that for sound, we specifically need a particle that vibrates and bumps into something else to transfer the vibration. You can't hear it. No, that's an electromagnetic wave. The radio converts it to sound, the mechanical sound wave. Yes, yes, yes. Okay. Say again? No, not conduction. No, 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 no. In your mouth, you compress air and you release it. So there's a compression and a rarefaction that travels through the air. It bumps into your eardrum and it vibrates, and your brain interprets the vibration as sound. Like a speaker changes it into sound that we can hear. Okay. But it is a mechanical wave. In other words, if I stood on the moon and I didn't have a radio set and I called to my friend standing a couple of meters away, will he hear me? There's no medium. One way of thinking about it, if you think of the sun, on the surface of the sun are nuclear explosions of hydrogen fusing with hydrogen to form helium. Major explosions. We see the light, we feel the heat. Do we hear the sound? Why not? There's a vacuum, and sound cannot travel through a vacuum. Do you understand? So sound waves are mechanical. The other ones that we've done are electromagnetic. They can travel through space. The properties of electromagnetic waves over here, transverse waves, can move through a vacuum in comparison to mechanical waves that cannot. What is the example of the mechanical wave? Sound. Okay. Yes. Waves travels in straight lines. They do. but they are, yeah, it just radiates out from where it has been formed. Okay, and then diffraction can occur and reflection can occur to make a change direction. All right. Human hearing is approximately 20 to 20,000 hertz. Some people can hear slightly lower and some can hear slightly higher. Usually the older you get, you start losing the ability to hear some of these very high frequency sounds. It's got to do with the elasticity of the tissue and the vibration. Sometimes people say they can't, when people talk, they can only hear certain parts of what is said, not the higher tones very often. Okay, that is just the elasticity of the tissue and the vibration. No, it differs from person to person. Yeah. Yeah, it is technically possible. I don't know how yeah. You can't go and say with every year you lose so many hertz. That's not true. Some people have excellent hearing up till old age, others don't. It depends on, yeah. Yes, yes. That's just what I wanted to say. Sometimes you walk into the homes. I know the old TVs also used to do it. They give off a high frequency. Some people hear it, some people don't hear it. Okay? Yes, it does. It drives you crazy. Yes, high frequency sound. No. In other words, you are able to hear slightly the higher frequencies. Dogs, a dog whistle, we can't hear it. The frequency is too high. Dogs hear the high frequency. Elephants communicate with very low frequency sounds. We can't hear them. The vibration is too slow, or the vibration is too fast, and the eardrum just goes, it can't vibrate. Do you understand? So we can't hear those sounds. All right. So the unit in which sound is measured is something called a decibel, and it's a logarithmic scale, which simply means for every increase of 10 units on the scale, the energy has doubled. Yes? It will probably not hear it. Yeah. It depends on the microphone, what it is set to pick up. Do you understand? It is also designed to be sensitive to certain frequencies. Yeah, so it might not pick it up. Okay? All right. An echo is a reflection of sound. When sound is reflected, the angle of incidence is going to equal the angle of reflection. We use this reflection of sound in medicine, all right? In sonar, when you want to have a look at a baby in the womb, they use sonar to look at your heart, to check to see are the arteries open, is the thickness of the wall, the size of the chamber, all right? It is simply sound that is reflected off the different tissues, and we have a computer that puts it into the image that we can interpret. I think it's low frequency, low energy. It doesn't affect the baby at all, or living tissue at all. It's not at all dangerous or invasive. Yeah, it doesn't. It's not dangerous at all. Okay. All right. They use it for echolocation in fishing trawlers. They have the fishing trawler, okay, and it will send out a pulse of sound. And here we have a school of fish, and the sound wave is reflected off this wall of fish. Bats. Bats use echolocation. Whales could also be, yes. Okay. Okay. Yes, they're using echolocation for blind people. They give them glasses with things that catches up reflections of sound, and they learn to navigate with it. Yes, they do. They do. Yeah, that is echolocation. Yeah. Bats people are expert navigators using echolocation. They are so good at it. A bat that is flying over here, it's got 2 ears, all right? And it gives off this pulse. Let's say it's hunting a moth. Then if the moth is over there, the sound that is reflected to this ear is caught up before the sound that is reflected to that ear. And he can navigate to exactly pinpoint the moth. Okay, it's excellent. The scientists don't exactly know how it works. Okay, but they are excellent echo locators. Also proven, interestingly enough, they don't always use the echolocation. They fly on memory as well. If they live in a cave that they move in and out of every day, scientists have gone and then they put up a net once they've left for the day. And then at night when they fly back, or in the morning when they fly out, they fly into the net because they are flying on memory of what it would be like you walking in the dark through a part of the house that you know. Okay. Bats use echolocation. Very, very interesting. Okay. Speed of sound. Speed of sound differs depending on the medium. On an average, speed of sound is 340 meters per second. Some texts say 333. What it comes down to, on a cold day when the air is more dense, sound will travel slightly faster than a hot day when air is less dense. All right. So speed of sound, when we work with it, they will give you a value or they will ask you to calculate a value, but it is not absolute. It's not like light that is 3 times 10 to the power 8 meters per second. Yes, yes, that's the Doppler effect. We'll be doing it soon enough, so I don't want to go there now. No, I want to carry on here. I don't think it will make that big a difference. I don't think so, because they're usually going to do it out in the desert. It's probably slightly easier if the air is very hot and less dense. Okay. All right. Speed of sound then is approximately 340 meters per second. At higher altitudes, what happens to the air? It becomes less dense. So what's going to happen to the speed of sound? It's slower. All right? So at higher altitudes, it will travel slower because the air is less dense. Remember, the sound is transferred when one particle bumps onto another. So if it's less dense, the particles are further away. It's harder to transfer the vibration. Then it can't transmit the sound. Then the sound dissipates and it's lost. Yeah, well, there isn't. Yeah. It will probably not be very good. Yeah. Okay. Although sound travels faster in denser air, the speed can become slower on a cold day. This is because the energy of the molecules is less. But basically, people, when the air is colder and more dense, sound travels faster. But there is a point, if it becomes so cold that the particles don't have enough energy, then they also can't vibrate. Do you understand? And bump. So in general, we accept colder air, sound travels faster. And the higher up you go in the atmosphere, the air becomes less dense, so sound travels slower. Okay. Yes. 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 Yes, yes. Helicopters also are designed for certain altitudes. Some of the helicopters, the smaller ones that we can use at the coast at sea level, can't be flown over here by us because the air pressure is less. Yes, it will definitely affect it. Yeah, yeah. Especially the smaller ones, no? The bigger ones that are more robust and have a higher output. Yeah. Yes. Yes. Yes, yes. Yeah. Yeah, yeah. There's a lot of engineering that goes into them. Ja, ja. Ja. Is dit waar dit begin het? Okay. All right, people, sound needs a medium to travel. Why? It's a mechanical wave. All right. Sound travels the fastest through a solid, then a liquid, the slowest through a gas. The fact that our ears are designed to hear in a gaseous medium doesn't mean it's the best medium for sound to travel in. If you put your ear on the desk and very lightly just drag your finger along the desk, then you can hear it. But over like this, you can't hear it. Yes, yes, it does. In your ear itself, from the gaseous medium, the eardrum vibrates, and then on the middle ear, what do we have? 3 little bones, solid medium that vibrates to amplify the vibration onto the inner ear, into a liquid medium. Okay? No, that's biology. All right? Yeah. All right. People, sound travels. All right, people, sound travels the best in a solid, then a liquid, then a gas. We can't hear very well in liquids if you're underwater, but you can still hear. Yeah, but not very well. But that is because our ears have been designed to hear in a gaseous medium. No, it's a limitation of the structure of the organ, not the fact that sound can't travel. No. All right. In terms of sound, if I have a very low voice, what does the sound wave look like? And if I have a very irritating high voice, what does the sound look like? When you are stressed, what happens to your vocal cords? What happens to everything? Tension. And if you pull your vocal cords, they vibrate at a higher frequency. What happens to the pitch of your voice? It goes up. I didn't do it. Yes, you did. Okay, people? In terms of what we hear, the pitch, high-pitched sounds, all right, have high frequencies, and low-pitched sounds have low frequency. If I could put it onto a sine wave generator, this would be the low-pitched. I didn't do it. Yes, you did. Is that one? High pitch, low pitch. In terms of loudness, the energy of the vibration is the amplitude. If you speak very softly, you will have a small amplitude. If you speak very loudly, there will be a large amplitude. If I drew a graph like that, that's my normal voice. And now I go and say to you, I want a low-pitched, loud noise. What would the graph look like? Low-pitched and loud. So, low for loud, I need a very high amplitude, but a low frequency. Yes, the wavelength will become longer. All right. Music versus noise. There is a scientific difference. Music has got regular, repetitive patterns to the sound wave. Noise has just got a jagged, random wave. And some of the music you listen to falls in that category. And that is damaging to the ear. It is. All right. People, that is resonance. We'll come to it. I'm trying to get there. All right. People, sound waves can be reflected. They can be refracted. Okay? On a cold morning, one can hear a dog barking from far. All right? Because the sound stays low on the earth. But on a hot day, it is refracted away and you can't hear it. Okay? So sound can also be refracted. Over here, we have interference of sound waves. Diffraction, it can bend around the corners of an obstacle. That's why I can hear Mr. Jan above me. Because it bends around the corners of the obstacle and it reaches me eventually. Interference of sound waves. Remember, for interference, we need the same frequency. So if I want to demonstrate interference of sound, I will need 2 loudspeakers and I will connect them to the same frequency sound. Okay? Then you will need a fairly soundproof room, and you will set up the speakers, and if you walked across the front of the speakers, you will find definite areas where the sound is louder and areas where it is softer. The parts where it is louder would be constructive interference. The parts where it is softer would be destructive interference. And the diagram will look exactly the same as the one for light or water waves. Yes, yes. When they build theaters, they design it, the engineers go and they design it with specific acoustics. That means it's designed so that there aren't dead spots at certain points. Or if they are, then there aren't chairs there. Then they'll have a pillow or something else there. No. The amphitheater in Rome was built in the time of Julius Caesar. That amphitheater, it's an open-air pit theater. So at the bottom is the stage and the steps going out to the sides, okay, are where the people sit. The acoustics of that theater is so good that when they stand down in the bottom and they talk, you can hear perfectly what is being said anywhere along that path. Yes. Okay. I don't know. Yes? With an amphitheater, yes, 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 yes. They are designed to be able to transmit the sound clearly. Yeah, well, yes. Okay. But probably when there's lots of people sitting there, the body's absorbed, then some of the sound gets lost. But they are designed to transmit the sound so that you can hear it. Yes. Yes. Okay. That is. Yes. Yes. Yeah. Yes. It's this. Well, yeah, because it's designed to absorb the sound because we don't want all funny reflected sounds. That is why when we watch a movie in the hall, the sound is not very good because the acoustics of the hall is not all that good. Okay. And then when there's a lot of people in it, the sound is absorbed even more and it makes it even worse. But the theaters and the stuff have specially been designed to be able to transmit the sound carefully from the stage to the rest of the auditorium. Okay. Now, the part that Johannes was on about, the Doppler effect. Okay. The Doppler effect is it's very simple. If I'm standing still and I am at a motor car racing event or bike racing event, and one car comes from far and it goes, what does the sound do? I don't want loudness. What else? High pitched as it's coming closer, and as it goes past me, the pitch drops. Have you ever noticed that? Okay? If a car with a hooter comes past at a high speed, the pitch drops. As it approaches me, the pitch becomes higher, and as it goes past me, the pitch becomes lower. Good question. Why? This is the Doppler effect. Now, the easiest is to show you with a diagram. Yeah, I'm standing. This ambulance is approaching me. But as it approaches me, it makes a sound wave, and then it drives into that sound wave, and it produces another sound wave. So look what happens to the frequency of the sound that I hear. It's higher. And if it goes past me, it's still making sound waves, but it's driving away from the sound wave that it has made over there. So if I am standing over here, as it approaches me, I get this compression that I will hear a higher pitch. As it goes past me, I get the rarefaction. I will hear a lower pitch. Okay? That's the Doppler effect. In terms of light, faraway objects. How do scientists know the universe is expanding? When they looked at light of these objects, the light is supposed to be white light, but they see red or blue light. If it's expanding, we are going to see a longer wavelength because it's moving away from me. Which one has longer wavelength? Red light. If an object gives off blue light, it's approaching you. And I'm talking about long distances now. If an object gives off red light, it's traveling away from you. If the original light produced was white light. Are you with me? All right. People, there's a formula. The observed frequency, FO, observed frequency, is equal to final plus initial velocity of the object divided by the velocity of the object, velocity of the wave, sorry. Depends on whether it's coming to you or going away from you. Are you going to see a longer wavelength or a shorter one? If it's going away from you, you will see a longer wavelength. If it's approaching you, you will see a shorter wavelength. No. Minus. All right, people. V is the velocity of the wave. U is the velocity of the source. For example, the ambulance. The velocity of the wave is a sound wave of 340 meters per second. And then divided it by the speed of sound. And then F is the frequency of the source. The frequency sound that was generated. All right. Please have a look at that. Yeah. Yeah. It's usually going to be 340 and 340 plus or minus the speed of the object.